You've probably heard that quantum entanglement only works in pristine laboratories, sealed off from vibration, temperature change, and the chaos of the real world. That's not true anymore. In 2026, researchers threaded entangled particles of light through the same aging, overworked fiber optic cables that already carry your Netflix stream, your bank transfers, and your late-night texts. And it worked. Here's how they did it, why it matters, and why the internet you're using right now has no way of doing what they just proved is possible. For decades, entanglement lived almost entirely inside controlled environments. Physicists built it in basements, shielded from stray light, on optical tables, floating on cushions of air to kill vibration, inside rooms where even a slammed door somewhere down the hall could ruin a delicate measurement. That care wasn't paranoia. Entanglement is fragile in a way that's hard to overstate. It describes a strange link between two particles, usually photons, where measuring one instantly tells you something about the other, no matter how far apart they are. Einstein hated the idea so much he called it spooky action at a distance, convinced that quantum mechanics had to be missing something, some hidden variable that would make the universe behave sensibly again. Decades of experiments have since shown Einstein was wrong about that particular objection. The spookiness is real, the correlations are real, and they don't travel through the fiber the way an email does, carried as a signal you could intercept and read. The entangled state exists as a single unified system stretched across distance, and that difference is the whole reason anyone cares about doing this outside a lab in the first place. To understand why researchers were willing to spend years and enormous amounts of money chasing this goal, it helps to understand what a network actually needs from the phenomenon. Entanglement by itself, sitting between two photons a few centimeters apart on a lab bench, doesn't do anything useful for communication. The value only appears once you can generate it reliably, send it somewhere useful, and confirm on arrival that it survived the trip intact. Every one of those steps introduces a chance for the fragile correlation to break down. Photons get absorbed by impurities in the glass of the fiber. They scatter off imperfections. They lose their precise timing relationship to each other as they travel through cable that isn't perfectly uniform along its entire length. Even something as mundane as a temperature change in a building can shift the properties of a fiber segment enough to throw off a carefully calibrated system. Multiply that by the length and complexity of a real city's infrastructure, and you see why physicists assumed for decades this wouldn't scale outside a controlled room. Because if you can only make entanglement work in a sealed room, you have a fascinating physics result and nothing else. You can't build a network out of a phenomenon that only survives inside a vault. A quantum internet, if it's ever going to exist, has to run through the same kind of infrastructure the regular internet already uses. Fiber optic cable buried under city streets, strung along utility poles, bundled together with thousands of other cables carrying ordinary data, exposed to sunlight, temperature swings, traffic vibration, and decades of wear. That's an environment built to be practical, not pristine. And for a long time, the assumption was that entanglement simply couldn't survive it. Too much noise, too much interference, too many chances for the fragile quantum state to collapse before it reached its destination. This year, several American research teams set out to test that assumption directly, not in a hypothetical simulation, but in actual cities, using actual deployed fiber that was already doing its job carrying real internet traffic. And the results have quietly rewritten what people thought was possible. Start with New York City, which has become something like the flagship testing ground for this entire effort. Researchers working with a company called Connect, alongside academic partners including NYU, built a live experimental network they call GothamQ, threaded through the city's existing telecom infrastructure. This wasn't a straight line between 2 points in a quiet suburb. This was Manhattan fiber, some of the busiest, noisiest, most heavily used cable on the planet, sharing conduit space with thousands of other connections, subject to constant vibration from subways and street traffic, exposed to shifting temperatures as it runs through buildings, tunnels, and exposed junctions across the city. Inside that chaos, the team successfully linked entangled quantum signals across 3 separate nodes spread across New York, using a technique called entanglement swapping. Here's the basic idea behind that technique, stripped of the jargon. You can create entangled pairs of photons relatively easily over short distances. The challenge has always been extending that entanglement further without it degrading into noise. Entanglement swapping solves part of that problem by creating 2 separate entangled pairs, then performing a joint measurement on 1 photon from each pair at a middle node. That measurement effectively connects the 2 remaining photons, which have never directly interacted with each other, into a new entangled pair stretched across a longer distance. It sounds almost like magic, and in a sense it is, but it's magic backed by rigorous mathematics, and now backed by real-world demonstration across an actual American city. One of the researchers behind the New York work explained why Manhattan specifically makes sense as a proving ground. The city is remarkably compact. Most of the relevant infrastructure sits within 5 or 6 miles of itself, and packed into that small radius are hundreds of financial institutions, hospitals, universities, and government facilities, exactly the kind of dense cluster of high-value targets that would benefit most from unbreakable communication security. If a quantum internet begins anywhere in the United States, the argument goes, it's more likely to start in a place like this than in a sparse, spread-out region, where the distances between nodes make everything harder and more expensive. It's worth pausing here to appreciate what entanglement swapping actually buys engineers building a real network, because it's the backbone technique behind nearly every serious attempt at a quantum internet, not just the New York experiment. Direct entanglement between two photons weakens the farther they travel, since loss in the fiber increases with distance, and at a certain point, the signal becomes too degraded to use. Rather than trying to force a single fragile pair of photons across an entire city in one uninterrupted hop, engineers can instead break the distance into shorter, more manageable segments, generate reliable entanglement across each shorter segment, and then use swapping at intermediate nodes to stitch those shorter links into one longer connected chain. It's conceptually similar to how classical internet traffic doesn't travel from your device to a distant server in one uninterrupted leap either, but instead hops through a series of routers along the way. The quantum version is far more delicate, since there's no simple way to just amplify a quantum signal the way you'd boost a classical one without destroying the very quantum properties that make it useful. But the underlying architectural idea, break a long problem into shorter, connected pieces, translates surprisingly well. The New York effort didn't stop at simply proving entanglement could survive the trip. A related demonstration involving Quennect and Cisco pushed the system's performance to levels that start to look genuinely useful rather than merely interesting. Using room temperature equipment, which matters enormously because cooling quantum hardware down to near absolute zero is expensive and impractical. Outside a research lab, the team achieved entanglement swapping rates exceeding 1.7 million pairs per hour under local conditions and more than 5,000 pairs per hour across deployed city fiber. A separate paper from the same broader research effort reported distributing polarization entangled photons across 34 kilometers of real New York fiber, hitting fidelity as high as 99%. Meaning the entangled state that arrived at the far end was almost perfectly intact compared to what was sent. Just as important, the system kept running. Over a 15-day stretch of continuous operation, the network maintained uptime above 99.5%, which starts to sound less like a fragile laboratory curiosity and more like actual infrastructure. That distinction matters more than it might seem at first. A one-time demonstration proves something is physically possible. Sustained, automated, high-uptime operation over weeks proves something closer to engineering readiness. It's the difference between a prototype that works once under perfect conditions and a system that keeps working while nobody is watching it day after day through whatever the city throws at it. New York wasn't the only city where this played out in 2026. Move west to Chicago, where a team at Northwestern University ran what might be the single most internet-relevant version of this experiment so far. Instead of using a dedicated, isolated fiber line set aside specifically for the quantum signal, they sent entangled photons through a 24.4-kilometer stretch of metropolitan fiber connecting Evanston to downtown Chicago, while that exact same cable simultaneously carried high-capacity commercial internet traffic, real data, real bandwidth, the kind of traffic that floods a shared line during a normal business day. That's the scenario that matters most for the future of this technology, because building an entirely separate, dedicated fiber network just for quantum signals across every city in the country would be staggeringly expensive and, frankly, unrealistic. The more compelling vision, the one that actually has a path to happening, involves quantum signals riding alongside classical internet traffic on infrastructure that already exists. Northwestern's team made that vision look achievable. Despite sharing the cable with heavy classical data transmission, they preserved entanglement fidelity above 94%. They managed this by keeping the quantum signal and the classical internet traffic in different parts of the light spectrum. The quantum data traveling in what's called the O band, separate from the C band typically used for conventional optical communication, and by synchronizing the systems with picosecond level precision, timing accurate to roughly a trillionth of a second. One of the researchers described the challenge with a memorable comparison. Sending a quantum signal down a fiber full of classical internet traffic is like sending an ant down a path filled with elephants. The quantum signal is almost unimaginably faint compared to the torrent of classical data around it, and yet the photons survived the journey, still entangled, still intact. The Northwestern team isn't stopping there either. Their next stated goal is quantum teleportation between remote nodes across that same live metropolitan network, still carrying ordinary commercial traffic the entire time. If that works, it pushes this technology another significant step closer to something that could eventually be layered onto the internet as it already exists, rather than requiring an entirely separate physical network built from scratch. These American demonstrations didn't happen in a vacuum, and it's worth being honest about that, because part of what's driving the urgency behind all this work is a broader international race. Researchers in China have pushed entangled photon distribution across roughly 260 miles of fiber, and China's Beijing to Shanghai quantum backbone already spans an enormous 2,000 kilometers, connecting major cities with quantum key distribution infrastructure that's been operational for years. European researchers, through initiatives like the European Quantum Communication Infrastructure Project, are building out their own continent-spanning quantum network ambitions. None of this is happening in isolation. The American city-scale demonstrations in New York, Chicago, and the D.C. suburbs represent the United States asserting a specific complementary approach to that same global effort, proving that entanglement can ride directly through existing metropolitan telecom infrastructure, sharing space with ordinary internet traffic, rather than requiring entirely new dedicated national backbones built from the ground up. Different countries are betting on different paths toward the same destination, and this year's results from these 3 American cities suggest the metro fiber approach has real legs. Then there's the Washington D.C. area, where a team at the National Institute of Standards and Technology took a different angle on the same underlying question. Rather than pushing for record-breaking distance, they focused on exposure. Their setup sent entangled photons through 62 kilometers of commercial fiber, connecting NIST's campus in Gaithersburg, Maryland, to the University of Maryland in College Park. On paper, that distance doesn't set any records. A European team had already pushed entangled photons across 248 kilometers of underground fiber years earlier. What made the NIST experiment noteworthy wasn't how far the signal traveled, but where it traveled through. A significant portion of that 62-kilometer path ran above ground, strung along poles and exposed infrastructure rather than buried safely underground. Above-ground fiber faces a rougher environment than buried cable. It experiences direct temperature swings between day and night, wind-induced vibration, physical strain from expansion and contraction, and general exposure to the elements in ways that underground fiber is largely shielded from. The physicist who led the study described the experiment as a stress test of quantum networking systems, a deliberate attempt to throw real-world messiness at the technology and see whether it held together. It did. The entangled photons survived the exposed above-ground stretch and completed the journey between the 2 research campuses, offering strong evidence that future quantum networks won't necessarily require the pristine, fully buried, carefully shielded infrastructure many assumed would be a hard requirement. Put these 3 American results side by side, and a pattern starts to emerge that goes well beyond any single city or research group. New York proved that entanglement swapping across multiple nodes can work reliably, at high fidelity with high uptime, inside one of the most electronically chaotic environments on the continent. Chicago proved that quantum signals can share a cable with heavy classical internet traffic without falling apart, using the same kind of infrastructure that already exists under every major American city. And the D.C. area proved that entanglement doesn't require the fully shielded underground-only conditions that once seemed necessary, surviving real exposure to wind, weather, and vibration along an above-ground route. None of these are separate curiosities. Together, they sketch the outline of something that starts to look like an actual blueprint. A future quantum internet, if it ever gets built at meaningful scale, probably won't require tearing up every street in America to lay brand new dedicated fiber. It will likely run through infrastructure that already exists, sharing space with the traffic already flowing through it, tolerating the exposure and imperfection of real cities rather than demanding laboratory-grade conditions everywhere it goes. That's a genuinely different picture than the one most people carry around in their heads when they hear the phrase quantum internet. And it's a far more achievable one. So why does any of this matter beyond the raw physics of it? Why should anyone outside a research lab actually care that entangled photons can survive a trip through Manhattan fiber, or share a Chicago cable with Netflix traffic? Start with security, because that's where the stakes are most immediate and most tangible. Nearly everything you do online right now, every password you type, every bank transfer, every private message, is protected by encryption built on mathematical problems that are extremely hard for today's computers to solve. Factoring enormous numbers, for instance, underlies much of the encryption securing the modern internet. That difficulty is what keeps your data safe from anyone trying to intercept it. But quantum computers, once they mature enough, are expected to be able to solve exactly those kinds of problems far faster than any classical machine ever could. That's not immediate. Building a quantum computer powerful enough to break today's encryption at scale remains a serious engineering challenge, likely years away. But security researchers don't wait for a threat to fully arrive before preparing for it. because encrypted data intercepted today could simply be stored and decrypted later once the technology catches up. That strategy already has a name: harvest now, decrypt later. This is where entanglement-based networks offer something genuinely different from anything classical encryption can provide. And it's worth understanding exactly why. Because the distinction isn't just technical marketing language. Classical encryption relies on a secret being mathematically hard to guess. If someone intercepts your encrypted message today and simply doesn't have enough computing power to crack it, the message stays safe, for now. But if their computing power improves later, or if a flaw in the math is eventually discovered, that same intercepted message becomes vulnerable retroactively. The secret didn't change. Only the attacker's ability to break it changed. Quantum key distribution built on entanglement works on a completely different foundation. Instead of hiding a secret behind difficult math, it relies on a fundamental law of physics. The simple act of observing a quantum system changes it. If someone tries to intercept an entangled quantum signal to read it or copy it, that interference leaves a detectable fingerprint in the resulting data. The two parties generating a secure key from that entangled signal can check for signs of eavesdropping using statistical tests grounded in quantum mechanics itself. If the results come back clean, matching the pattern expected in the complete absence of an eavesdropper, they know the key is secure, not because breaking it is difficult, but because any attempt to intercept it necessarily disturbs the system in a way that gives it away. That's not a stronger lock. It's an entirely different kind of security, one that doesn't degrade as computers get faster, because it was never built on computational difficulty in the first place. A future quantum computer, no matter how powerful, doesn't help an attacker defeat that kind of protection, because the protection was never a puzzle to be solved. It was a physical law being enforced. That's the part classical infrastructure genuinely cannot answer. You can make classical encryption more complex, add more computational layers, lengthen the keys, and buy yourself more time. But you can't make classical bits do what entangled photons do, because classical information can be copied without disturbing the original, silently and undetectably. Entangled quantum states cannot be copied that way. Any attempt to intercept and clone the state necessarily disturbs it, a principle physicists call the no-cloning theorem. And that disturbance is precisely what exposes the eavesdropper. It's not a matter of better software patching a weakness. It's a completely different category of security, rooted in something the classical internet, running on ordinary bits, simply has no mechanism to replicate no matter how sophisticated it becomes. And security is only the most immediate application. It's the one getting the most attention because it maps cleanly onto problems people already understand. But it's far from the only reason researchers are pushing this technology out of the lab and into real cities. A working quantum network could eventually link separate quantum computers together into something far more powerful than any single machine could be on its own, distributing computational tasks across multiple quantum processors, the same way classical computing clusters distribute workloads across many linked machines today. That kind of distributed quantum computing could tackle problems that remain out of reach even for the most advanced individual quantum computers currently being built, from modeling complex molecules for drug discovery to solving optimization problems that grow exponentially difficult as they scale. It's also worth understanding what quantum key distribution looks like in practice, because the phrase can sound abstract until you break it down into what actually happens between two parties trying to communicate securely. Picture two people, traditionally given the placeholder names Alice and Bob, in nearly every paper on this subject, each holding one photon from an entangled pair generated somewhere between them, or delivered to each of them through entanglement swapping across a longer network. Each of them independently measures their photon using randomly chosen settings, and afterward, over an ordinary public channel that anyone could listen in on, they compare notes about which measurement settings they used, without revealing the actual results of those measurements. Wherever their settings happen to match, the underlying quantum correlations guarantee their results will match too, and those matching results become the raw material for a shared secret key. Crucially, they can also run a statistical check on a portion of their data, testing whether the pattern of correlations matches what pure, undisturbed entanglement should produce. If an eavesdropper tried to intercept the photons along the way, that interference would show up as a measurable deviation from the expected pattern, alerting Alice and Bob before they ever rely on a compromised key. That's the mechanism NIST, Northwestern, and the New York teams are ultimately building toward whether or not a given experiment ran the full protocol start to finish. Entanglement distribution is the hard physics problem. The security layer on top is comparatively straightforward once reliable entanglement is available. There's also the emerging field of quantum sensing, which tends to get far less attention but carries enormous potential of its own. Networks of entangled sensors can achieve a level of collective measurement precision that isolated unconnected sensors simply cannot match, because the entangled correlations between them provide additional information that separate independent measurements can't capture. That could eventually mean more precise timing systems for navigation, more sensitive detectors for scientific research, or improved geological and environmental monitoring, all built on networks of instruments linked by the same kind of entanglement now being tested across New York, Chicago, and the D.C. suburbs. None of this means a fully functional quantum internet is arriving next year, or that you'll be sending quantum encrypted texts to your friends anytime soon. The challenges that remain are still substantial. Entanglement remains fragile by nature, and every kilometer of additional fiber introduces more opportunities for the delicate quantum state to degrade before it reaches its destination. Scaling these systems up from a handful of experimental nodes in 3 cities to a nationwide interconnected network involves enormous engineering effort, significant cost, and years of continued refinement. The equipment required, while increasingly practical thanks to advances like room temperature operation, still needs further development before it can be deployed at the scale a truly national network would require. And meaningful coordination between researchers, telecom companies, and government agencies will be necessary to eventually connect these separate city-level testbeds into something larger and unified. But here's what changed this year, and it's worth sitting with for a moment, because it's easy to breeze past just how significant this actually is. The core assumption that entanglement could only survive under laboratory conditions, isolated from the mess and unpredictability of the real world, has been directly and repeatedly disproven, not in theory, not in simulation. In actual American cities, using actual deployed commercial fiber alongside actual internet traffic, under actual real-world conditions, including vibration, temperature swings, and direct exposure to weather. That barrier, once considered one of the more serious obstacles standing between quantum networking and practical reality, has been crossed, and crossed multiple times by multiple independent teams using different approaches in different cities, all within the same year. The classical internet you're using to watch this video right now runs on bits, ones and zeros, that can be copied, intercepted, and read without necessarily leaving any trace behind. That's simply how classical information behaves, and no amount of clever engineering built on top of it changes that fundamental fact. Quantum entanglement offers something classical bits cannot replicate, not because engineers haven't figured out a clever enough workaround yet, but because the fundamental physics involved is genuinely different in kind, not merely more advanced in degree. For most of the history of quantum research, that difference stayed locked inside laboratories, demonstrated on optical tables, shielded from the outside world, treated more as a fascinating curiosity than a practical foundation for anything. That changed this year. New York proved the networking piece works reliably at meaningful scale. Chicago proved it can share existing infrastructure with the internet you already use every single day. And the DC area proved it can survive genuine real-world exposure rather than requiring pristine, fully controlled conditions. Put together, those 3 results represent one of the more concrete, tangible steps yet taken toward a genuinely different kind of internet. One built not on mathematical difficulty that erodes as computers get faster, but on a law of physics that doesn't change no matter how powerful those computers eventually become. Whether that new kind of internet arrives in 5 years, 15 years, or through some path researchers haven't fully mapped out yet remains an open question, and reasonable experts disagree on the timeline. But the foundational question of whether it could survive outside a lab at all, exposed to the real, messy, imperfect infrastructure that any nationwide network would actually require, has been answered this year in 3 American cities, using the exact same tangled, aging, overworked fiber optic cables running beneath the streets you walk every single day.